TA evaluation form. Bring it back Thursday or someday when the TA is not here, because that's kind of awkward. The TA will be going through a review next Tuesday. You're going to have your exam on Thursday. I won't be here all that week, but it'll be similarly proctored, except maybe we'll print them a day before so you guys actually get them on time this time. Maybe. So any questions? You have a homework here and then another homework due Tuesday. So hopefully the exam will go a little bit smoother, because I think these homeworks are a little bit harder. Yeah. Yeah, we'll post the homework solutions for both homeworks no later than Tuesday afternoon. These we'll try to get up quicker than that, but I'm saying both homeworks will be up by next Tuesday afternoon, which is when the second homework is due, the 7th homework. Any other questions? Okay. So the topic that we were on last time is what we're going to pick up today, and it was about multiple steady states. And so we had these two equations. What do these equations represent?
Generation and removal.
Yeah, this is the amount of heat generated as a function of the temperature. And this is the amount of heat removed from the system, also as a function of the temperature. And so if I plot the amount of heat removed as a function of temperature, what does that plot look like? Does it? Do you see delta H in that equation? No, I was saying the heat removed. Yeah, let's worry about RT first. It's a straight line. What's the slope of that curve? In other words, what is dr dt equal to? All right, Cp naught 1 plus kappa. And so as you increase kappa, this line becomes more and more vertical, right? And so why do we know that that's linear without looking at the form of the equation? Why is that a straight line? What does the amount of heat removed depend upon? Heat capacity, yeah. So that shows up. What's the driving force for heat removal from a system? A temperature gradient, right? So if I'm plotting the amount of heat removed versus the temperature, you would expect a straight line. The hotter the reactor, the larger the driving force to remove the heat from the system. Okay, and what about the heat of generation term? What shape does that curve have? Does it? Does the shape depend on anything? R. The rate? Yeah, but it'll always have a similar shape.
So it's also linear?
No. It's not linear. It's curved, right? What is this shape called?
Sigma.
Yeah, this is sigmoidal. Or it's an S-shaped curve, right? And so if I have three intersections, then what do I have? What do these intersections represent? Steady states. And so obviously in this case we have multiple steady state solutions. Why does the sigmoidal shape, why does the heat generation term have a sigmoidal shape? No, it's not because it's an autocatalytic reaction. This applies to any reaction. Simple first order reaction will have that shape. It's based on conversion. Yeah, it's certainly related to conversion, but why, just in words, why would it have a shape like that? Because the rate, say that louder. Oh, because the rate will have the same curve. Yeah, I mean that is the only thing that's changing here with temperature. So that is true. But why does it have that curve?
I think that helps reverse nicely, but as the temperature is low, you're not going to like your decay cost is not going to affect stuff as much.
Okay, so I think what you're saying is that if you're down here in the low temperature region, then maybe not a lot of reactions taking place. And as you change temperature, the effect of changing the temperature is not that dramatic. A similar thing happens up here. Why?
So you're limited by.
What happens to an exothermic reaction as you run at more and more, at hotter and hotter temperatures, to the total amount of heat generated by that reaction?
Pushes it to the reactants because of the exothermic, because of the heat produced.
You're thinking about reversible reactions in an equilibrium, but this doesn't need to be a reversible reaction. So up here, you're going to start being near X equilibrium or 100% conversion if it's irreversible. And so changing the temperature a little bit more is not going to change the total amount of heat. The total amount of heat released from the system, right? The total amount of heat released is still, how much heat would be released if you did 100% conversion? That's all that you're doing up here is you're changing from 99.9% conversion to 99.99% conversion. That's it. So you're not making a big impact in the amount of heat that you have, that you're releasing from the system. And then of course in this region is where you have small changes in temperature can have a big impact on the total amount of heat released. And so what is the total amount of heat released? It's nothing but the conversion times the delta H of reaction. So as you go to higher and higher conversions, you get more and more heat released. The temperature that you start at affects the conversion that you end up at in a way that gives you that shape. So just have a feeling for where do these shapes come from. It's not specific to a certain type of reaction or anything like that. Any reaction can have this sigmoidal shape. And the heat removal term is always going to be a straight line if you're just considering, you know, a fairly standard heat exchanger or heat loss to the atmosphere. It's always going to be a straight line. So these systems are not unique. This can happen to just about any reacting system that's not run isothermally. Okay, so we have three different steady states. But you can imagine that I have a curve with two steady states. So what is this point? It's not TC. It's not that. But we called this T star, right? It was the tangential temperature. And what's true at that tangential point? First of all, G is equal to R because it's an intersection. So any intersection on there, you're going to have G equal to R. That's just the definition of an intersection. But what else is true at that tangent point? The slopes are also the same. And as we said, the slope of dr dt, I erased it. And hopefully you guys can see where that comes from. That one is fairly simple. This slope is a little bit more complicated. First, does delta H reaction at standard condition change with temperature? No, right? Does the volume of the CSTR, the PFR, anything? No, right? Does the initial flow rate? No. So the only thing in here that can change with temperature is the rate equation. So it's simply equal to all that stuff. Right? And so then we can approximate this. So what changes in our rate equation with temperature? Let's just take a very simple first order reaction. What changes with temperature? K changes. What else? Anything?
Sometimes concentration.
Sometimes the concentration. Which one changes more? K. And so we can approximate this as simply the change in the rate constant with respect to temperature, which is A. Don't give this one.